In this video, we will be discussing about addressing modes, its definition, types, why we need them, and its uses. In order to understand the concept of addressing modes, we first need to have a clear understanding about what instruction is and the format of the instruction that is passed to the computer. So what are instructions? Instructions are binary coded commands that directs the CPU to perform a specific operation or task, and it also specifies how the data is going to be processed, transferred, or manipulated. So here we have the general format of instructions, and it has three major components, which is the opcode, addressing mode, and operands. The opcode is the part which tells the CPU what is the action it needs to perform, and it can be of any form like adding or multiplying the numbers or just moving the data. Next, we have the addressing mode. The addressing mode tells the CPU about the location of the operand and how we are going to be accessing these operands. Next, we have operands. Operands are the values or the data on which the operation specified in the opcode will be performed. Now, let's elaborate more about addressing modes. Addressing modes are the techniques or methods which is used by the CPU to identify the data that is needed for the operation. The operands of the instructions can be located either in the main memory or in the CPU registers. If the operand is placed in the main memory, then the instruction provides the location address in the operand field. Many methods are followed to specify the operand's address, and the different methods or modes which we are using to specify the operand's address in the instructions are known as addressing modes. There are many ways in which the operand's address will be specified in the instruction, and here are some common methods which will be discussed in this video. First, we have the implied mode. In implied addressing mode, the operand is implicitly specified by the instruction itself. The CPU already knows where to find the data, so no extra addresses or registers is needed. An example for this in the assembly language will be the CMA. The CMA is the complement accumulator, which calculates the complement of the values which is in the accumulator. Here, the operand is implied because CMA always operates on A. In order to have a clear understanding about this, let us consider a real-life example for this, which will be the flipping of light switches. So, the switch always controls the same light, and we need not specify which light is to be turned on or turned off. We just press the switch and the light state changes automatically. And this is what we call as the implied mode. We have the immediate addressing mode. In immediate addressing mode, the operand is directly given in the instruction itself instead of being stored in a memory or a register. So the CPU doesn't have to look anywhere else. It just uses the value that is provided in the instruction. Also, immediate mode is the fastest addressing mode because it bypasses the need for memory access to retrieve the data. The example instruction given here is load R1, 100. Here, the hash symbol is used to represent the value of the operand. So, the value 100 will be directly loaded into the register R1. Next, we have the direct addressing mode. In direct addressing mode, the instruction specifies the memory address where the operand is stored. Instead of directly using the value of the operand, the memory address is given. So, the CPU fetches it from the given location. An example instruction given here is load R1, 1000H, where 1000H refers to the address of the operand. So the CPU goes to the memory location 1000H and fetches the value from there and then loads it into the register R1. The direct addressing mode is also known as the absolute addressing mode. The next addressing mode is the indirect addressing mode. In the indirect addressing mode, the instruction specifies the register or another memory address which will be containing the original address of the operand. So the CPU first fetches this address, then moves to the original address of the operand and fetches the value from there. And here The example instruction given is load 1000H. So 1000H refers to the memory address, which will be referring to the original address of the operand, and the value will be fetched from the original address and loaded into the register. Next we have the register addressing mode. In register addressing mode, the operand is stored in a CPU register, and this instruction directly refers to the register instead of the memory, which will make the execution faster because the CPU doesn't have to access the memory. And the example instruction given here is load R1, R2. Here, the value will already be existing in the register R2, and CPU will move the value from R2 to the register R1 without accessing the memory, which makes the execution faster. Next, we have the register indirect mode. In register indirect addressing mode, the instruction specifies a register that contains the memory address of the operand. So, the CPU first fetches this address from the register and then retrieves the actual data from that memory location. An example instruction given here is load A, R1. Here, the register R1 holds an address, let's say 1000H. Then the CPU first looks at the register R1, fetches the address, and then retrieves the value from the address 1000H and loads the value into the register A. Since the register contains the address of the operand and not the operand itself, it allows for dynamic memory access. The next addressing mode is the indexed addressing mode. In indexed addressing mode, the operand's address is calculated by adding a base address which is given in the instruction and an index value which is stored in a register, and it is commonly used for accessing the arrays or list in the memory. The example instruction given here is load A, 1000H and R1. Here 1000H is the base address and R1 gives the index. The CPU calculates 1000H plus R1 in order to get the actual memory location of the operand and then loads the value from there into the register A. In order to have a clear understanding, let us consider a real-life example for this, which will be finding a seat in a movie theater. We will be having the row number and the seat number. In order to find our exact seat, we will add the seat number to the row's location, which helps us to quickly locate the specific seat in the series of seats. And it is similar to accessing the array elements. This is what we call as the indexed addressing mode. Here we have the auto increment addressing mode. In auto increment addressing mode, a register holds the memory address of the operand. After accessing the operand, the CPU automatically increases the register value to point to the next memory location. This is useful for reading data sequentially, like processing elements in an array. The example given here is load A, R1 plus. Here, the CPU fetches the value from the memory location which is stored in R1. After fetching, it automatically increases R1 to point to the next memory location. Next, we have the auto decrement mode. In the auto decrement addressing mode, a register holds the memory address of the operand. Before accessing the operand, the CPU automatically decreases the register value to point to the previous memory location. This is useful for processing the data in the reverse order, like reading the elements from the end of an array. And the example instruction is load A, minus R1. The CPU first decreases R1 to point to the previous memory location. Then it fetches the value from that memory location into A. So we have seen the different types of addressing modes. Now, why we need them? Firstly, they provide flexibility in data access. By using the different addressing modes, we can access our data in various ways according to our needs. Also, they reduce the instruction size by minimizing the number of bits that is required to represent the address. Then, it also simplifies the programming by implementing different structures like counters, pointers, and indexing. They also offer efficiency in code execution by giving quicker access to the data that is stored in the contiguous memory locations. Moving on to the uses of different addressing modes. The implied addressing mode is used in the single operand instruction where the operand is predefined by the instruction. Example, stack operations and the accumulator based operation. The immediate addressing mode is used when the operand value is fixed and known during the compile time. For example, setting initial values, counters, and constants in programs. The direct addressing mode is used when accessing the specific memory locations directly. Example, reading the status registers, simple variable access in small programs. And the indirect addressing mode is used when the memory locations are dynamic and they need flexibility. For example, pointer-based programming and accessing larger data structures dynamically. Then, register addressing mode is used for the faster execution since the data is in the CPU registers, for example, arithmetic and logical operations. Register indirect addressing mode is used for the efficient memory access when dealing with arrays, linked lists, and pointers, for example, dynamic memory access and table lookups. The indexed addressing mode is used for array processing, loops, and table lookups, where an index determines the exact memory location. For example, accessing the elements in arrays and strings in loops. The auto-increment addressing mode is used when sequentially accessing the data like in loops, buffers, or stacks. For example, reading the stream of data. The auto-decrement addressing mode is used for reverse order processing, such as stack operations and traversing arrays backwards. For example, the LIFO concept in the stack popping.